which the title of my thesis was "The Search for Ultra-High Energy Neutrinos with Amanda 2." Why neutrinos? So traditionally, we observe the universe optically, so visually. Naked eye, then people started using binoculars and eventually telescopes. And most of the knowledge we still have today about the universe comes from these optical observations. So it's either visible light, UV, IR, X-rays, gamma rays, but it's something that's false. It's transmitted by photons. That's the primary source of information. Photons are good carriers of information in the sense that there's a lot of them, and they're easy to detect. How do you detect photons? You see them with your eyes, right?
Or on them.
I use this thing.
There's a little bit of a... Chris? Thank you. The problem is, though, that they're absorbed by interstellar matter, such as dust and gas. So, good thing, lots of them, easy to detect. Bad thing, they tend to disappear on the way. And that's why it's hard to observe things that are far away in the universe where there are. If something is behind another planet, we're not going to see it, right? That's why we have the neutrinos, because they're awesome. Neutrinos are almost massless, so they have hardly any mass at all. They're also neutral. And they don't like interacting at all with stuff. They're like the most introverted, shy little particles you can ever imagine. At a party, you would find them in the corner hiding. They don't like interactions. And what's cool about that is that they're really good at carrying information. They're not going to be stopped on the way. They can carry information from really far away, go straight through planets, and come all the way to the Earth. The only downside is that they're really hard to detect. It takes 1 light year of lead to stop a neutrino. That's a lot. You can't really picture it. So what you end up doing is you can't actually catch the neutrinos themselves, but you can see their tracks. So it's a bit like tracking animals. Finding the tracks in the snow, you don't have to see the fox, but you see the tracks and you know that a fox passed. This is how. So, in my work I focus on one. Relax, Chris, you'll be alright. They're different elementary particles. The neutrinos belong to the family of elementary particles. And there are different flavors of neutrinos. And out of all the different neutrinos, I only looked at muon neutrinos. That's the Greek letter for mu. So a muon neutrino can interact with a nuclei and create a muon and some leftover stuff. Or you can have the anti-muon neutrino interact with nuclei and create an anti-muon. Are you okay? Or are you gonna pass out?
I think my brain's about to explode.
I know. I was like, oh.
Very, very simple.
Bring on the rubber
Neutrino
sheet.
Stuff kicks out muon and stuff.
And that's the track that you're following.
So I can't detect this one.
Yeah.
But when this reaction happens, I can detect this one. That's the cool thing. And have you ever seen those pictures from nuclear reactors with the blue light?
No.
There's something called Cherenkov radiation. You can just Google it. So what happens when a particle moves faster than the speed of light in the medium is you get a bow wave of light. It's like when a boat moves through water or a plane goes faster than the speed of light, sound. You get just this wave after it. And you get the same thing with light. And that's what happened in a nuclear detector. In a nuclear power plant, it's just that the particles are moving through water faster than the speed of light in the water. So the particle is sort of outrunning its own light track behind it. And this blue field here represents Cherenkov radiation from this muon. So I can't detect the neutrino. I actually can't detect the muon either, but I can detect the Cherenkov light that the muon emits. So it's kind of a 3-step process. And to do that, you use photomultiplier tubes. It's just like inverted flashlights. Instead of sending out light, they detect light. And by instrumenting a big volume, you can detect the Cherenkov radiation, and you can see where the neutrino moved through the detector, and then you also know where the neutrino went, because they actually have the same angle, so the tracks kind of overlay. Super simple, right? So if you're gonna catch something very rare, you have to cast a very wide net, so you need something that's really, really big. The neutrino telescopes have to be huge. And actually they have to be really, really big. we're trying to detect light, so not only we need a detector that's big, we also need a detector medium that's transparent so we can actually see the light. And one thing you can use is ice. So this represents the detector I worked on. It's at South Pole in Antarctica. And Antarctica actually has a bedrock underneath, but then it's 3 kilometers of ice on top of the bedrock. And the whole detector is deployed in the ice. So we took hot water and just sprayed it down for 3 kilometers to open up a hole. And then we deployed strings with these light sensors in the ice, like beads on a pearl necklace. And then it all refreezes, and when the particles move through the ice, we can detect the particle tracks. So it's 1 cubic kilometer big. So it's a kilometer by kilometer by kilometer. Running budget about $400 million per year.
I could get as much hot water there.
Do they need QA?
Hot water.
Actually, no.
Or drinking a lot of beer.
And this is what the data typically looks like. What you do is you detect the electrical signal from these all these photomultiplying tubes, the light sensors. And just the color of them and the size tells you how close the track was, how powerful the signal was. And then you can just try to fit the track to your data. And that type of data analysis was kind of what I did. So that's the building where I worked, and that's actually a Swedish flag, which is pretty cool. So that's geographic South Pole. I have proof.
That's sort of you.
That's my name title. That's the building I worked in. That's the outhouse, because there were no proper bathrooms in the building I worked in, so I used the outhouse.
No.
That's flying on an LC-130, which is a Hercules plane.
That's inside the
Which is a
outhouse.
transportation.
Big box.
That's a smooth ride when there's not a lot of passengers on the flights, you can actually move around. A Hercules plane is not big, but it takes up to 64 passengers, and then you're packed and you can't move at all, and it's horrible. This is what the light detectors look like. So they're encapsulated in really thick glass, because imagine what the pressure is like 3 kilometers below the ice, right? So they have a circuit board. They each actually have their own IP address, so you can ping them and talk to them individually. And I built a lot of those, the circuitry, and assembled these modules, because you also have to be really, really tight, airtight and watertight. And the cables are pretty thick, because again, they carry the weight of 3 kilometers. That's what the electronics look like when it comes up from the surface. It's a big mess. It's fun to try to track which signal goes where. And just other cool pictures. Hercules plane, but if you're lucky early in the season, you can fly the jet plane, which is an LC-40. Compared to the Hercules prop plane, that's like a luxury flight. It's really awesome. Questions?
Oui.
Oh,
It may sound rude, but
Oh no.
Oh, he's
somebody-
prefacing it.
why did somebody think it was important?
because fundamental science and research is what teaches us about life and everything, and it brings on so many benefits that we don't know about in advance. Very few of the big discoveries that have helped humanity progress have been deliberate. Next.
So there.
Yeah.
Graham, you got a question?
Chris goes first.
Where do neutrinos come from?
Good question. Look what I have for you.
Thank you very much.
Is it signed? Check, make sure it's signed.
You generate 340 million neutrinos per day.
Oh, I think he
Smell more.
I think he produces more.
Oh, that's a smell. Yes.
So, the thing's really big, the detector. Like, I'm genuinely fascinated by this. So, my questions are stupid, I know, but I am genuinely fascinated. Like, how many neutrinos like go through that then? Like,
Another book.
Oh, I thought you were just going to hand him the book back.
Let's imagine this is the Earth.
yeah.
We're being hit by particles from the universe all the time. Most of them get stopped by the atmosphere, because there's a lot of reactions and there's cosmic rays that are just bombarding us. But there's a lot of muons created in the atmosphere, and they create a background that we're not interested in. So what IceCube does is that it looks through the Earth, because the only particles that can go through the whole Earth and get down to IceCube are neutrinos. all the other particles will be filtered out. So Ice Cube uses the Earth as a filter. And the neutrinos we're looking for are coming from ultra high energy events like supernova, dark matter, etc. So your neutrinos, we don't care about. They're low energy. Sorry. And if you look at Art McDonald, who won the Nobel Prize last year, he works at Snow Lab, which is a completely different type of neutrino experiment. They also look at low energy neutrinos from the sun and other phenomena. Whereas IceCube is completely focused on high energy and only detects a couple of neutrinos per year in this cubic kilometer volume. That's how rare those events are. You're talking about single-digit numbers in a year in a cubic kilometer volume.
So like the high energy ones only come from like the massive events in the universe.
And the only ones we can have react in this big detector, or that do react, there's just a couple of them. That's how weakly interacting they are.
So like two particles,
Once you refreeze your line of neutrino detectors, how do you do maintenance?
It is somewhat sketchy. If something breaks, it's gone forever. And the scariest events I've ever had was, so they run on high voltage, of course, like 5 kilovolts, and you have to ramp the power up slowly so you don't blow the electronics in those modules. And there's a script that does that automatically, so you just start the script and it starts ramping the voltage up in certain steps. You don't have to do that manually. But one year when I was there in Antarctica,